Ordinarily, I wouldn't do a worked through question outside of the normal movies, but seeing as how a lot of people have a hard time with Arrhenius questions, I thought it would probably be a good thing to do. So anyway, let's look and see what we've got here. First order reaction, don't really care. Rate constant at a given temperature. There's activation energy, there's rate constant at a different temperature. Now, anytime you see activation energies, rate constants, and temperatures, you can assume there's something to do with the Arrhenius. Natural log of K, the rate constant, natural log of A, the Arrhenius constant, minus the activation energy over R, the jolly old gas constant, times T, which of course will always be in Kelvin anytime you're messing around with the gas constant. Now, what we have here is we actually have two temperatures. So it's two sets of conditions. So let's put in generic letters into the Arrhenius equation for that. So we'll say we've got one set of conditions, the rate constant is K1, the temperature is T1. At the second set of conditions, the rate constant K2, the temperature T2. And notice that the Arrhenius constant, activation energy, and R are constants for that given reaction. Now let's do some pretty color coding here. So our first set of conditions, 45 degrees Celsius for the temperature, rate constant 8.54 times 10 to the minus 4. Let's pop them in to the first set of conditions. So there we are right there. And now the second set of conditions, we know it's at 25 degrees Celsius, but we don't know the rate constant. So we'll pop that in there, don't know the rate constant, so we'll call it K2. The temperature is 298. Now what we have here is we have two equations in which we got constants and constants and constants, and then we've got one value of K, unknown value of K, two values of temperature. So what we can do is we can combine these two equations together to hopefully get rid of at least one of the unknowns. And the best way to do that is to get rid of log of A, because nobody really cares about log of A. And the best way to get rid of log of A is to subtract the two equations. Now I could subtract them in the order I've done now, but that would put that log of K2 as sort of the secondary thing, if you see what I mean. So let's keep that as the superstar subject to the question and subtract the second equation from that. So I'm going to do this equation minus that equation. Left-hand side will be natural log of K2 minus natural log of 8.54 times 10 to the minus 4, just like there. Right-hand side, well, the log of A minus log of A cancels out. So I'll get minus the activation energy divided by R times 298 right there. And then a minus of a minus, so that means plus EA over R times 318. Now, putting this together a little bit, anytime you got log of a log, you know that it's the quotient. So that becomes log of K2 over 8.54 times 10 to the minus 4. And on this side, I'm pulling out the EA over R right there. I'm actually going to pull out plus EA over R. So that will leave me with minus 1 over 298. That's the minus 1 over 298. And over here, plus 1 over 318. That's the plus 1 over 318. Make sure you're happy with what I've done there. Now, I still haven't put in the value for the activation energy. Some people would leap ahead and put in 90.8, but please notice that R, 8.314, is in joules per mole per Kelvin. So therefore, the activation energy must also be in joules. So the number we'll put in is not 90.8, it is 90,800 joules. So now pop all this into our calculators. Let's put this in first, and that number comes out to being minus 2.305. Now we'll get rid of that nasty natural log by doing e to the power of. So e to the power of this just cancels out the e to the power and the log n, so it becomes K2 over 8.54 times 10 to the minus 4. E to the power of minus 2.305 is 0.0998. Now we just multiply out and we find that K2 is 8.54 times 10 to the minus 5 seconds. Now, does that make sense? Well, we know that it's 45 is 8.54 times 10 to the minus 4. We would expect it to be smaller at 25. Indeed, it is smaller. It's not hugely different in the main number, but look, it's 10 to the minus 5 instead of 10 to the minus 4. So that's one type of nasty little Arrhenius question where you're given rate constant and one temperature, rate constant, It's one type of question where you're given two temperatures, one rate constant, the activation energy, and asked for the rate constant at the other temperature. The other type of question is where you're given the rate constant and temperature stuff and asked for the activation energy. Now I could do one that's exactly like that, where I give you K1, K2, T1, T2, you splash it all in and get EA, but I'm going to do something a teensy bit different just to extend you. So here it is, a question I wrote back when I was living in Houston, and I used to love breakfast burritos from Taco Cabana, particularly those with chorizo, egg and cheese. But I must admit, sometimes I would buy quite a few, leave one out, and it would go off. So I'd stick it in the fridge and it would go off, but much more slowly. So let's see what we've got. Okay, I'm asked for an activation energy. I'm given a couple of temperatures, so it must be to do with the Arrhenius equation. Let's throw in our data at the different conditions, K1 at T1, K2 at T2. Now I know T1 and I know T2, so let's throw those in there. So log of K1 is log of A minus EA over R times 278. Log K2, log of A minus EA over 302. Okay, now what I'm going to do is I'm going to combine these in the same way I did before. I'm going to subtract this top equation from that bottom one, put it together. I'm not going to take all the time I did before. So log of K2 minus log of K1 is log of K2 over K1. Pull out the EA over 8.314, and I'm left with the minus 1 over 278, or actually, excuse me, it's minus 1 over 303 minus 1 over 278, so that's 1 over 278. Okay, now the trouble is though, I'm asked for the activation energy, but silly person as I am, I didn't give you the rate constants. But what I did do was I gave you the time, and rate and time are inverse. Okay, so the longer it takes, the smaller the rate. Okay, the shorter time it takes, that means it's happened more quickly, so the faster the rate. Now when I look here is that as I go from 5 degrees to 30 degrees, it takes 5 times shorter. Okay, so if the 5 times shorter, then that means that the rate is 5 times more quickly. So it's going 5 times more quickly at 30 degrees, that's the K2, than it is at 5 degrees, that's the K1. In other words, K2 over K1 equals 5. Okay, make sure you see that. Here's the higher temperature, it's going to be going more quickly. It takes a fifth of the time, which means it's going 5 times as fast. Okay, so K2 over K1 is 5. Pop that in here, so log of 5 is EA, this nasty little thing here, 1 over 278 minus 1 over 303, divided by 8.314, it's 3.57 times 10 to the minus 5. So EA is 45,000 joules per mole, or 45.1 kilojoules per mole. Hope that kind of makes sense. We'll do a couple more during the live session, and if you missed the live session, then a little while after the live session, when I said a little while, it'll be days rather than minutes, there will be a worked through PowerPoint. Hope to see you then.